So what's a finite state machine? We start with, it's a set of states, of all things, a finite number of them. One of them is special. It's the start state. There is a set of transitions that tell us how we move from one state to the next. And note that you can move from one state to itself or to a different state. And then how do we tell which transitions to take? There's an input alphabet. You can think of it as symbols like A's and B's. You can think about it as events in the world. It's a discrete set of things. And we label the transitions. So you can see we've labeled A's with these with A's and B's. And now the question is, what does one of these machines do? And there are a couple different versions, but let's first talk about the version whose job is to say this input string, this input sequence of events is legal. We're looking for something. We're looking for some pattern. And we'll mark the states that are accepting here with an extra circle. We're going to feed inputs to the machine, one symbol at a time. And when this input sequence is over, we're going to say yes if we land in an accepting state, sometimes also called a final state. And we're going to say no if we land someplace else. Okay? So in this case, we're going to start in state 1. And let's imagine that the input sequence is ABA. So we start in state 1. The input symbol is an A. And so we take this transition from state 1 to state 2 because it's labeled A. All right, the input remaining is B and A. We're now in 2. We're going to read the B. And note that there are 2 transitions from 2, one labeled A and one labeled B. We'll take the one that's labeled B, and we will move to state 4. We now have only one input symbol left to read, and we're in state 4. It's an A, and we're told that we should loop back to 4, so we cross that off. We loop back to 4, and now we're out of input. We're out of input. We're in state 4. State 4 is accepting, and so we say yes. All right, now you might think, why did we care? Why did we care about some sequence of A's and B's? Now let me give you a somewhat more realistic example. Consider this case. We have children's soccer teams, and children enroll, and the rule is that a legal team has to contain at least one boy and one girl. So we start here in state 1, and we have no children. If a girl shows up, then we're going to go here to state 2. If a boy shows up, we're going to go here to state 3. And then if we keep getting girls, we stay in 2. That's the case where we only have girls. We're not legal yet. If we keep getting boys, we stay in 3. And then if we're in 2 and we see a boy, we go to 4. Same thing if we're in 3 and we see a girl, we go to 4. And now we're in a state where we have at least one boy and at least one girl, and that's our accepting state. At this point, add some more kids or don't, you have a legal team. Okay, so let's just kind of, here's our machine, bigger. Let's watch this one in action. If the input is simply girl, then we go here. We started here, we go here, we're in this state, and we don't have a legal team. Okay, now suppose that the input were girl, 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 girl. Well, then we go here, and we loop for the second one, and again, and again. Note that we're in the same state with 4 girls as we were with 1 girl. We don't care how many girls. From the point of view of this problem, we don't care. 1 girl, a zillion girls, you've got the required girl. Suppose, on the other hand, the input were girl, girl, boy. Well, now we're going to go girl, girl, boy. And now, if that's it, we have a legal team. State what we numbered 4 before corresponds to the case of at least 1 boy and at least 1 girl. And we can do another one. 4 boys takes us boy, 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 girl. Note that we don't care whether the boy signed up first or the girl signed up first. State 4 remembers only one thing. There's at least 1 boy and at least 1 girl. And that's the fundamental property of these finite state machines. They throw away most of the history except whatever you need in order to make a decision, which in this case is at least one of each. Now, there are real physical finite state machines all over the place. I like to think of this as a wishful thinking vending machine because, as you'll see, it reaches its accepting state here, 2 circles, on 25 cents. You can't buy much of anything for 25 cents. But let's look at what's going on. The start state here is 0. You've put no money in. If you put in a nickel, you go to 5. If you put in a dime, you go to the one labeled 10. The labels don't matter, except they help us understand what's going on. If you have a quarter, you go directly down here to 25. But if you had a dime and then another, and then a nickel, and then another dime, you also get to state 25. State 25 doesn't care. 1 quarter, 2 dimes, and then a nickel, a dime, another dime. The order in which you put in your money doesn't matter. In this case, the only thing that matters is the total amount of money. And by the way, we have this special symbol here. I've labeled it $sign. That means push the button and get a Coke. And at that, you can only do that from state 25. You'll note that there aren't any such transitions anywhere else. And that takes you back to state 0. And by the way, one of the cool things about this formalism is that it's a great documentation tool. If you asked me, well, what if I put in 3 dimes? And then that would get me here, and then I push the give me a Coke button, do I get to go back to state 5, so I have 5 cents left and I can get another one? And the answer, if you look at this machine, is you go directly back here. If somebody wished to design a more friendly machine, they could certainly do so. But the formalism lets us see exactly what's going to happen. Here's another simple example. You want to sell Viagra, and the spam filters want to try to prevent you from selling Viagra. And so all the spam filters have a property that if they see you write that, then they throw the message away. So the spam generators have figured out that you don't actually have to write Viagra. You could, for example, recognize that somebody is going to, if they see the 2 slashes, it's going to look a lot like a V. So they can change the string to make it possibly get through the filter, but the filter guys are smarter, and they build a finite state machine. So you can go from the start state to the second state with a V, but you can also do the same thing with a slash and a slash that goes the other way, and you get here, and it doesn't matter. Now, from here, you've got the V equivalent, and you can now do all the different I's. You can also, they've noticed that if you stick asterisks in the middle of strings, people tend to ignore them, and they'll still think that you wrote Viagra. So the other thing that somebody could have, a spammer could have done, is inserted an asterisk and then an I-type character, and now you're there. And note that that part is independent of whether you did this or this for the V part. And if you continue this machine, one person has written out a machine like this for a variety of variants, and you get 600 gazillion different ways to spell Viagra, but you don't have to write them out, all the combinations. That's the power of the machine. Now, there's a second kind of finite state machine. So far, we've seen ones whose job is to say, I found the pattern I'm looking for. Legal soccer team, Viagra equivalent string. The other thing we can do with the same notion of states is to simply display the sequence of states that we're in, or alternatively, the transitions. But let's just look at the sequence of states. And a classic example for this is a traffic light. There are 3 states. You're in the green state, you're in the yellow state, you're in the red state. And often in these machines, the thing that causes you to go from one state to the next is not a specific symbol, it is simply some elapsed time. So this is a really, really trivial traffic light. You're in the green state, 70 seconds elapse, you go to the yellow state, 10 seconds elapse, you go to red, and then 80 more seconds elapse, and you go to here. And the thing that the machine does that's useful is it simply displays to us what state it's in. We can make it a little bit more fancy. For example, fancier lights have the property that you can either wait 80 seconds to go from red to green, or you can have an emergency vehicle show up and it has a special button. And if it pushes that button, then we go from red to green. And you can add walk lights and whatever. But the point is that there's a finite number of states, there's a set of transitions, and in this case, we simply observe them. And that's useful to us. Most board games are finite state machines. So suppose, for example, that I'm over here, my little shoe is on Pacific Avenue. The state is I'm in Pacific Avenue. I don't care how I got there. I don't care how many times I went around the board. I am in Pacific Avenue. That's the only thing that matters to determine what's going to happen next. If I'm in Pacific Avenue and I get a 4, then I go here to short line. If I get a 2, I go to community chest. If I'm on North Carolina and I get a 2, I can go to Pennsylvania. And once I'm at short line, again, I don't care whether I got there from Pacific Avenue or Marvin Gardens or whatever. We capture only that part of the past history that affects future behavior. So the essence of an FSM is that we partition the input sequences into sets such that if two strings share all possible futures, no matter what happens next, it's going to happen to both of them, then they land in the same state. And you can think of the states here, for example, as simply being the positions on the board. In the case of the vending machines, it's the amount of money that you've got. So the essence of an FSM is that it partitions the possibly infinite number of inputs into a finite collection of groups such that strings are in the same group in case they share a future. So here's a state of the soccer machine that groups together girl, girl, boy, boy, girl, 5 boys and then a girl, because they're all legal no matter what happens. They share a fate. Similarly, nickel, nickel, dime, nickel is equivalent to dime, nickel, dime because all of these share a fate. If you push the give me a drink button, it's going to work. So we design these machines. We can write them using notations like what we just saw, and there are tools that let you do that. And then once we've got that, we can actually build something. We can build a machine. We can build a traffic light. We can build computer circuits that are built in exactly this way. We can build software systems like spam filters once we've designed the machine and set it up in this way.